live now. It is my pleasure to have today with us Michal Feldman from Tel Aviv University. Michal is a great, fantastic researcher on the interface of computer science and economics and game theory. She is also jointly appointed with in Microsoft Research in Israel. She received her PhD from UC Berkeley in 2005. She has been later a visitor in Microsoft and Harvard. She is an associate editor of Games and Economics Behavior, Mathematics of Operations Research, AC and Transaction of Economy on Economics and Computation, and Journal of Computer and System Science. She will be telling us something today about profits, secretaries, online algorithms, and matchings. So I'll let her to take the floor. And let me actually still say something. If there are any questions during the talk, please put them in the chat, and I will just try to read them to Michal. She will most likely not have opportunity to see the chat, but I will follow this closely. So Michal, please go on.
Okay, thank you very much. Thank you for inviting me, and thank you for the nice introduction. Very happy to be here and to talk about all these terms that that Arthur mentioned: profit, secretary, online algorithms, matching, etc. Most importantly, this is based on joint work with Tomer Ezra, Nick Ravin, and Jihao Tang. So let me start by a really quick introduction to online algorithms. So here is a lady. She's in San Francisco and she wants to get to Yosemite. So she's waiting to catch a ride. This is the hitchhiking game. Oh, and let me just say up front, usually I use Zoom and they can see faces. It's really strange for me that using this system, I do not see your faces. So I apologize in advance. I cannot hear you or see you. So this is a one-way communication. This talk is meant to be more interactive, but unfortunately, this is not going to be this way today. So I apologize for this. Anyway, I'm happy to take questions that Arthur will say loud from the chat. Okay, good. So this lady wants to get to Yosemite Park, and she wants to catch a ride. And the first car arrives and she needs to decide, and the driver tells her, I'm going to Stockton, and she needs to decide whether to catch this ride or not. Stockton is too far from Yosemite. The next car arrives and this car is going to San Jose, way too far. And then the next one arrives going to Groveland, and she's like, okay, this is close enough, not quite the place I want to go, but who knows what's going to happen in the future. And she takes this ride and gets to Groveland. Okay, what she didn't know is that the next car that arrived went directly to the Yosemite Park. And this is, of course, an online setting where we have to make a decision now, not knowing what's going to happen in the future. And these are type of push or luck scenarios, and it happens a lot in our life when we have to decide about whether to accept a job offer or not, or a ride, or choosing a secretary, or choosing a PhD student, or a mentor, depending on what side of the universe you are right now, or an Airbnb apartment, and even a partner for life. So these decisions can be really serious. And as algorithm designers, we want to design good algorithms for such scenarios. So today I'm going to talk about two very well-known models in this world. One is coming from profit inequality, and I'll refer to it as profit. And the other is coming from the well-known secretary problem, and I'll call it secretary. I'll first present the very basic models of profit and secretary, and then I'll show you some extensions to matching in graphs. First, I'll do one-sided matching in bipartite graphs, and then I'll extend it to matching in general graphs, and I'll put more emphasis on these extensions, which are newer. And okay, there are two different models. So of course, this is an online problem. So elements arrive online. In one version, the vertices of the graph arrive online. And in the other one, edges arrive online. And this talk is going to concentrate on the model where vertices arrive online. Okay, but let's start where it all started, just the very basic setting. This is optimal stopping theory. We have a sequence of n values, v1 to vn, initially unknown. The values are revealed online, one per round, and we have to make decisions. So for example, maybe the first award is 1,000, and we have to make a decision either to stop the game, in which case I take the $1,000 and go home, the game ends, and I win $1,000, or I can decide to continue the game, in which case this prize is lost forever. I can never go back, and the game continues with the next box. Okay, so my decisions are immediate and irrevocable. So maybe the next one is $4, and again, I have to make a decision, and so on and so forth. And it's not very difficult to observe that in the absence of additional information in this very adversarial world, not much can be guaranteed. And more precisely, there is no algorithm, deterministic or randomized, that can give me more than 1/n approximation to the optimal value. So now, how do we handle this bad result? We are going to present two different models that are that belong to the world of beyond worst case in different ways. The first one is profit. Here, so in each one of them, there is something playing for us, which is beyond the worst case. In profit, what's playing for us is that the values are drawn from known probability distributions. I know the probability distribution from which the values are drawn, and the arrival order can still be worst case. And the mirroring model is the secretary model, where the values are still adversarial, just like in the fully adversarial setting, but they are assumed to arrive in a random order. Okay, so again, two different beyond worst case models. One is profit, and whenever you see this figure of the profit, you know that it's a profit setting. In the profit setting, we know the underlying distributions. That's the extra information we have. And this side is the secretary, where the items are assumed to arrive in a random order. Okay, but the values may be adversarial. Good. So let's be a bit more formal. We have n values, just like before, arriving online, v1 to vn. Let's denote the arrival order by pi. Alg is a possibly randomized stopping policy. Now we're just choosing a single element, so the algorithm just needs to make a decision when to stop. And alg v pi is the value accepted by alg on the sequence v under the arrival order pi. Opt v is the maximal value on v, okay, just the maximal value in the sequence. And we are going to measure the performance of our algorithm by the common performance measure of competitive ratio. So the competitive ratio is just the ratio between the performance of the algorithm and the performance of opt. Okay, so let's just be more specific about what's the competitive ratio for the two models. So in the profit, the competitive ratio, rho of alg, is the ratio between the expected performance of the algorithm, and the expectation is taken here with respect to the random values drawn from known distribution f. I didn't mention it, but I'm going to assume throughout the talk that f is a product distribution. So every value vi is drawn independently from some distribution fi. Those distributions may be different, but they are independent. And I'm going to take the worst case order. So I'm going to take the minimum over pi. Pi is the arrival order. And here I have the just the expected value of opt, which is just expectation over values of opt V, of the maximal value of V. So this is the competitive ratio in the profit setting. Now, in the secretary setting, the competitive ratio is the ratio between the expected performance of ALG, and the expected performance of ALG now is with respect to the random arrival order pi. So here pi is assumed to be random order. And in the denominator, we have opt V, which is just the maximal value of V. And now we don't have any expectation because this is just the value, and the values are adversarial. And I'm going to take the minimum such ratio over all possible sequences V. Okay?
Michal, there is a question in the chat. Let me just read it from Paolo Turini. What is the rationale behind taking worst case orders and adversarial values? Also, given the motivating example, is this a reasonable assumption, or does it make sense to consider alternatives?
Okay, so the question refers to the profit scenario where I'm going to take worst case order. So first of all, so I have two answers. One is that usually in computer science, we are very used to worst case analysis. Usually, like the first thing we always do is worst case analysis. So this is going in the direction of the standard worst case analysis thing. And as I said in the beginning, like if you're going all the way worst case, then if you're going all the way worst case, then we're taking both worst case of value and worst case of arrival order. And now these two models, we are trying to isolate the effect of each one of these worst case. So in one, we are taking expectation over values, but we want to isolate this effect. So we want to keep the arrival order worst case. And in the other, we are taking the adversarial values, but relax the assumption of worst case order. So this is some way to isolate the effect of these two assumptions. And also I should say that, these are for robustness. The reason to take worst case is for robustness. I cannot assume anything about the arrival order maybe. So yeah, let's just take worst case and see what we can guarantee. And of course, if we have good results, if we can find positive results even for worst case order, these are very good news. So I agree that in the world, we shouldn't believe that we'll get the worst case order, but we have positive results even in the worst case. This is the rationale usually behind worst case analysis. Okay, so this gives me a very robust result.
Okay.
Great. Thank you for the question.
Yeah, go on, please.
Okay, great. So usually at this point in the talk, I just play with the audience. Maybe I'll just play with Arthur.
Oh, no.
Yeah,
go on.
Okay, so Arthur, let's play the profit version of the game. So let me remind you, in the profit version, you know the underlying distribution. So the first prize is uniform 2040. The second is uniform 2040 as well. The third is uniform 1050. And the last one is uniform 070, okay? And this is just a coincidence that all of them are uniform. Of course, any other probability distribution is valid. And let me make it, because you're so nervous, let me make it easier for you. This is the arrival order, okay? I tell you the arrival order in advance. So now what's the game? I tell you the value, okay? So I just drew a value from this distribution, 33, and you have to decide, are you taking this 33 and going home, or you keep playing?
Do I know the number of arrivals?
Sorry?
Do I know how many will arrive?
Yeah, these are exactly the four.
Oh, okay, so I know, okay. Yeah, I'll be waiting.
Waiting, okay. How about now?
I would not be waiting. I still would be waiting, of course.
Still waiting, okay. 36.
Yeah, I would go for it.
36, you're going for it. Okay, so this is, I think, a reasonable decision, right? I mean, Arthur ran some algorithm in his head and decided to take the 36. Maybe, I guess what he did is he said, okay, the expected value here is 35 and this is greater, so yeah, let's take it. Yeah, In fact, if you would have waited, but yeah, how could you know, right? Okay, this is just to give you a sense of how these games look like. Now let's go to the results that are known in this world. Okay, so what I'm going to do throughout this talk, I'm going to fill out this table one by one. Some of these results are very classy, going way back to the early 70s, and some are newer. So what the profit scenario, the classic scenario where you only have to choose one element. So one can get 1/2 competitive ratio of 1/2. Okay, so in expectation, you get at least, there is an online algorithm that gives you at least 1/2 of the expected optimal value. And this is tight. Okay, if we have time in the end, I'll show you. This is a very simple example showing that this is tight. And in the secretary, as probably many of you know, in the secretary, the best competitive ratio one can get is 1/e. Okay, and this actually goes back to the 60s. So we have these two very beautiful results, 1/2 for profit, 1/e for secretary, and both results are tight. In terms of the algorithms, both of them are threshold-based algorithms. For the profit, we have a very simple algorithm that gives us this very nice guarantee of 1/2, which is just to calculate a threshold. And this threshold is based on the known distribution f. We know the distribution, we calculate a threshold based on f. In fact, there is more than one way to calculate a threshold that would give us 1/2. And then we just accept the first value that exceeds tau. Okay, extremely simple. For the secretary, it's also a simple algorithm, usual explore exploit. We start with an exploration phase where we just observe some initial elements, right? In the secretary setting, what's playing for us is the random order, so it's very natural to observe some values to learn what's a good value. And then in the exploitation phase, we take advantage of what we learned, and we take the first value that exceeds the threshold tau, which is set to be the highest value in the exploration phase. Okay, so these are the two algorithms that give us the 1/2 and 1e guarantees respectively. But then computer scientists started to look into this world. And of course, as computer scientists, we care about more complex situations and just general feasibility constraints. So in this new area, that has become very popular in the last decade or so, we are extending these scenarios, both profit scenarios and secretary scenarios, beyond choosing a single element. We are given a collection of feasible subsets of elements, and we can accept any feasible subset. Okay, for example, maybe we are given some matroid structure, and as the decision makers, we are allowed to choose any independent set in the matroid. And the goal is to maximize the sum of values of accepted elements. Okay, and this is something that I want to emphasize, because those of you who are familiar with the secretary problem, in the secretary problem, usually the more standard objective function is to maximize the probability of taking the maximal value. And now I'm going to change the objective. The 1/e works for both objectives in the classical setting, but the objective function that we are going to study today is to maximize the expected value of those elements I chose. Okay, and I can only choose a feasible subset according to the feasibility collection that I'm getting. Okay, and these extensions have been studied in many settings: matroids, polymatroids, intersection of matroids, knapsack, downward closed settings, combinatorial auctions, etc., etc. And the most relevant for my talk today is matching in graphs. Okay, so matching in graphs, what it means is that we have edges. Edges are the elements. And at every point in time, we must ensure that the set of edges we selected, form a matching in a graph. And matching in a graph is a very fundamental model with many applications. Let me just name a few. We can think about items and buyers in e-commerce applications, or matching drivers and passengers in ride-sharing platforms, or jobs and workers in online labor markets, etc., etc. In many settings, we have some bipartite graph and we want to do matching. So this problem comes in two flavors. One is edge arrival. Edge arrival is the more standard model, because I told you the elements are always the edges. So the edge arrival is the standard model where elements arrive one by one. And the other flavor is vertex arrival. In vertex arrival, the arriving elements are the vertices. So at every point in time, some vertex arrives, and I get to observe all the edges coming out of this vertex. Okay, so this, we can think about it as a batched model where elements, edges, which are the elements, arrive in batches. And they arrive in batches in a very natural way, where a batch is just the edges that are connected to a specific vertex. Okay, and as I said before, the goal is to maximize the expected weight of the chosen matching. If there are questions, feel free to type them into the chat. It's important that we'll be on the same page before I keep going. Okay, good. So let's start with one-sided matching in bipartite graphs, and let's do the profit version here. And you can just think about the equivalent secretary version in your head. So we have a weighted bipartite graph. We have the offline side, which let's call it items. So this is the offline side. And we have the online side, which is the agents, which are the agents. So that's why it's called one-sided matching. Every edge E has a weight WE, which is drawn independently from a known probability distribution FE. Initially, the WEs are unknown. We don't know the weights, but we do know, as in every profit setting, the underlying distribution. So here is an example. Maybe the first edge, the weight of the first edge is uniform 0.3, and the second one is Bernoulli 0.5, etc., etc. And then, upon arrival of a vertex V in L from the dynamic, from the online side, the weight, so maybe this vertex arrived, we get to see the weight of its edges. So maybe they are 1 and 7, and we have to make a decision. Now, the decision is not just whether to accept or not, but if we want to do a matching, we also have to decide which edge we are doing the matching on. So one valid decision, for example, is to choose this 7 weight edge, and this is an irrevocable decision. Okay, so maybe I chose it, and then the second vertex arrives, I get to see the realization, its neighbor is already blocked, so I keep going. The third vertex arrives, I see the realization, and I choose another edge, and I'm done. Okay, so this is just the model. This is just to show you what the setting is like. And I'm looking for an algorithm that will give me a good competitive ratio, okay? And I'm comparing myself to the expected optimal matching, given the underlying distributions. Okay, so let's continue to fill out this table. What's known about competitive ratios for one-sided matching in bipartite graphs? For profit setting, the exact same bound, 1/2, can be also obtained in this matching problem, okay? And of course, this is tight because just the bad example from the classical setting can be encoded in one-sided matching where I have, one vertex, one offline vertex on one side, and the n online vertices arrive one by one. So this is precisely the classic algorithm, the classic setting. So 1/2 is tight. What about secretary? Exactly the same bound, exactly the same competitive ratio, 1/E can be obtained in this setting. And again, it's the bad example carries over, so 1/E is tight. And this is due to a beautiful paper of Kesselheim et al., which I really like. It's a like very extremely simple algorithm with beautiful analysis. So if you haven't seen it, I encourage you to read it. And let me tell you very briefly how these two algorithms look like. So again, the techniques are still threshold based. So for profit, this in order to obtain the 1/2, the best way for me to think about it is as a market. I already alluded to it by calling it items and agents. So let's think about the offline side as items and the online side as agents. And the weight of an edge is the value that the weight of edge ij is the value that agent I has for item j, okay? And then the agents arrive one by one in worst case order. And the way the algorithm works is to set prices to items once and for all in the beginning, based on what? Of course, on what we know, which is the underlying distributions. So we set prices, static prices that never change to items, to the static items. And then upon arrival of an agent, and every agent is unit demand, meaning that he only goes on with a single item, the agent arrives, he observes all the values to items, and he chooses the item that maximizes his utility. The utility being the difference between the value on the edge and the price of the item, okay? And agents that follow this strategy, so this algorithm gives us a 1/2 if we choose the prices correctly, okay? So there is a way to choose prices so that this algorithm, which I described to you, gives a competitive ratio of 1/2. One nice thing, which you can think about it in your head, is that the classical algorithm, the classical threshold algorithm, can be viewed as a special case of this algorithm. So one way to view this algorithm is a natural generalization of the classic profit algorithm. And in the secretary setting, this is again a generalization of the simple algorithm in the classic setting. Again, we do some exploration. We observe some initial elements. So we have the static items, we have the dynamic side. We observe some elements as they arrive, some vertices as they arrive. We observe the edge weights. And then in the exploitation phase, what we do, upon the arrival of a vertex, we compute the the maximum weight matching of the graph that we have so far. And we match the arriving vertex to its partner if the partner is available. That's the whole algorithm, okay? And if you think about it for a second, you realize that the original algorithm is a special case of this algorithm, okay? So these two algorithms are natural extensions of the original settings, and they give us the exact same competitive ratio for one-sided bipartite matching. Okay, and one thing to note is that in all of these algorithms that I showed you so far, we are playing in the value space. We have these threshold-based algorithms where we are looking at value space and make decisions based on these values. And this is going to change. That's why I emphasize it. Okay, and now we are starting to generalize even more. We want to go beyond one-sided bipartite matching. For example, maybe we have a bipartite graph, but we have two-sided bipartite matching where both sides are dynamic. For example, drivers and passengers, there is no reason to assume that we have one static side and only one side is arriving dynamically, because both passengers and drivers arrive. So we can think of a model where we have a bipartite graph and every time a vertex from either side arrives. Or even more generally, in some settings are not even captured by any bipartite graph. Maybe we have a general graph and we want to do matching in a general graphs. For example, maybe we want to pair students into roommates, or maybe we want to do kidney exchange. So we have an underlying general graph and vertices arrive online. Every time a vertex arrives, we get to see its edges to vertices that have already arrived in the past, and we have to make a decision about matching, Okay, and those of you, and I assume many of you have worked on matching algorithms in the past, so you know that usually matching in general graphs is much more challenging than bipartite graphs, and this is also the case here. So I'll show you later, we have some new challenges that arise in general graphs. So we cannot adopt previous algorithms from bipartite graphs. Good. So I think this is a good time if there are to have a break if there are questions. No questions. Good. Okay, so now we are in this last line of the table. And we are all, I hope you are curious, as I was before writing these papers, about competitive ratios for matching in general graphs. So remember, for both prophet and secretary, we got exactly the same competitive ratios where we went from the classic setting to one-sided, and the question is, are we going to keep being lucky? Good. So for prophet, okay, and as I told you, the model is that upon arrival of a vertex V, we need to decide whether and to which former vertex to match V. We only see edges to former vertices. So for prophet, we give an algorithm, an online algorithm, that gets a competitive ratio of 1/2, even for general graphs, for matching in general graphs. But the algorithm is quite different than previous algorithms. So we try to extend previous threshold-based algorithms from the one-sided matching version, but we failed to match the tight bound of 1/2. So we had to go into a different algorithm that just works in more on the probability space than in the value space. And I'll show you the algorithm in a few minutes. Okay, good. So this is 1/2 for prophet. And then we got lucky again for prophet. So we got more appetite and we wanted to solve the secretary problem. Okay, so what's the best thing we could have hoped for in the secretary setting for general graphs? Of course, we hoped to match the bound of 1/e. Good. That was our initial hope. Eventually, what we got is 5/12. Okay. We actually got better result than 1/e. So this is a bit confusing, what's going on here. How come the 1/e is not blocking us? And the reason, if you think about it for another second, you realize that because of the random order, the competitive ratio for one-sided matching in bipartite graphs is not an upper bound on the competitive ratio of the matching in general graphs. For example, here is encoding the classical bad example in one-sided matching, where I have one static vertex, and these vertices arrive dynamically, these n vertices arrive dynamically, and I get the 1/e. But with this example, I cannot really get 1/e as an upper bound if I'm doing general graphs or two-sided arrival, because when this vertex arrives, maybe it's halfway through, and I already get, but just here is a very simple algorithm that gives me already 1/2 for this specific example. Just wait until this vertex arrive and match it to the best vertex so far, right? This already gives me 1/2, and I can actually do better for this specific instance. So that gives you the intuition for why this 1/e is not binding us. And the answer is 5/12, and this 5/12 is tight. And I'm going to show you both the upper bound and the lower bound for this result. Okay, good. So I see there are no questions in the chat, which probably means that I can keep going. Okay. Oh, yeah. And by the way, We also have results for the other model that I mentioned, which is the more standard model, where the edges arrive online, not the vertices. And we have some improved results also for edge arrival. So for profit, we were able to break the 1/3 competitive ratio that was known before. And for secretary, we were able to improve from 1/2e to 1/4. But today I'm not going to talk about these results. They appear in the papers if you're interested to look at them. So I'm going to concentrate on this line, matching for vertex arrival. Good. So let's do profit first, and then let's do secretary. So here is the algorithm for profit. As I told you, it's working on the probability space. Good. So here is how the algorithm works. So first of all, I calculate these values xe for every edge e. I calculate the probability that e is in opt. For example, and this is our running example, this symmetric triangle. So for this symmetric triangle, xe is 1/3 for all edges e. Okay, because it's all symmetric, so every edge is in opt with probability 1/3. Then, upon the arrival of a vertex, and in fact, let's directly go to the second vertex, because as I told you, I only see edges to previous vertices. So upon the arrival of a vertex, let's denote by BV the batch of vertex V, which are the edges from V to former vertices. These are the blue edges. For example, in this example, this is the blue edge. And negative BV minus BV are the red edges. These are all other edges. Okay, for example, here, these are the 2 red edges. And what I do, I observe the weight of the blue edges, right? This is the setting. I sample the weights. I do fresh samples from the underlying distributions of the red edges. And now I calculate the max weight matching of the weights, those that I observed, the blue one that I observed, and the red ones that I sampled. And potentially I have a partner to this vertex V. In this case, it's 1. This is the potential partner in the max weight matching. If we have a partner which arrived before vertex 2 and this vertex is available, the partner is available. Remember, the partner may already be taken, but if it's available, then I want to match it. That's the algorithm, but not quite. I do some hedging. And what I do, I only match it with a certain probability that I call alpha UV, which is this expression here that depends on the x's. Okay? And I want you to notice that I can only calculate these alpha UV online upon the arrival of a vertex V because I don't know the order, the arrival order up front. Okay? And why do I do this hedging? The intuition is that I want to keep vertices available for future rounds with a sufficiently high probability. So I don't always match when I can. Okay? Good. So for example, here I match only with probability 1/2. Maybe I didn't match and I keep going and I'm doing the same thing, observing the new edges, sampling the other edges, and doing max weight matching and match with some probability that is calculated by this alpha UV. That's the whole algorithm. So now, maybe I matched it. So one more thing to notice, this probability is valid. It's at most 1 because this sum here, this is the sum of XRU for a particular vertex V, R smaller than V. So because we are doing matching, this sum is smaller than 1. So this probability is smaller than 1. And indeed, it's a probability. Okay, so let's do the analysis. So let me remind you, what I'm going to show you is that this algorithm gives me a competitive ratio of 1/2. So I get, in expectation, 1/2 of the expected optimal matching. For the sake of analysis, let's imagine I had a different algorithm which did exactly the same thing, but if we had a partner, I just match it. Okay, I don't check for availability and I don't do this hedging. And
Michal,
yes.
There is a question in the chat from Gleb Polevo.
Mm-hmm.
How do you know minus B sub V if those vertices haven't arrived yet?
Okay, great. So great question. So let me remind you the setting. The setting is that I know the underlying distribution. So I know the underlying, this edge, I know the underlying distribution up front. This is a profit setting. So I just sample from the distribution. I don't know the weights, I just sample the weight. Okay, the graph is known in advance and I know all the underlying distributions. So I just sample from the distributions. And one thing to notice is that even edges that so for example here, remember at this stage when vertex 3 arrives, I already know even the weight of this edge because I already observed it. And still I do fresh samples from the distribution, and this is important for the analysis. Okay, so I always do samples from the edges other than the new ones, even if I know their weights. Okay, now as I said, we are going to do the analysis, and let's imagine I always match if possible, and even if the partner is not available, and let's call these edges the provisional edges. And of course, this algorithm is not feasible because it might give us a set of edges that do not form a matching, but this is just for the sake of analysis. Okay, so here is the analysis in 3 lines. So the first lemma is that the probability that an edge E is provisional is exactly XE, is exactly the probability that E is in opt. Why? Because we sampled exactly from the same distributions. The second lemma is the core of the analysis, and this is where these alpha probabilities get in. The second lemma says that the probability that E is matched, given that E is provisional, is exactly 1/2. Okay, so if I want to match an edge, the lemma here says I match it exactly with probability 1/2. And the way to see this is by induction. So first of all, I can calculate the probability that the partner U is available. And here I use the induction hypothesis to say that this is exactly this expression here. And now you see that I chose alpha UV to be such that this conditional probability is exactly 1/2. Okay. And then the third lemma is a refinement of the first lemma, saying that the expected value of the provisional edges is exactly the expected value of opt. Again, this is just by design. And lemma 2 plus lemma 3 together gives us the conclusion that this algorithm gives us a competitive ratio of 1/2. Okay, this is the whole analysis. Good. Now let me use the remaining time to show you some results for secretary. So as I told you, I'm going to show you a competitive ratio of 5/12, which is tight for matching in general graphs for the secretary matching. Okay, so first of all, as I mentioned before, doing matching in general graphs in the secretary setting is more challenging than in one-sided bipartite graph, partly because in the one-sided bipartite graph, in this beautiful paper of Kesselheim et al. That I told you, the analysis goes by establishing an upper bound on the probability that an offline vertex is matched. Okay, we have the offline side. And in the analysis, we set an upper bound. We make sure that every vertex is available in future rounds with a sufficiently high probability. However, in general graphs, we don't have this nice separation between offline side and online side, and there are some non-monotone dependencies between matching probability of vertices. So for example, the event that a given vertex is matched can be either positively or negatively correlated with the event that another vertex is matched. And for this reason, an upper bound is not sufficient, and we have to compute precise probabilities that given vertices are matched or not. Okay, so let me show you how we do it. So here is the algorithm, and without loss of generality, assume that the maximum matching is unique. You can just do some perturbations. Right, so just like in every secretary algorithm, we start with an exploration phase. Notice that this time the exploration phase is longer, usually both in the classic setting and in the one-sided version. We observe for n over e, this is the exploration phase, and now we are going to observe n over 2 of the vertices. So we wait until half of the vertices arrive and we do nothing. Then, upon the arrival of vertex vt, the vertex that arrives in time t, which is greater than n over 2, so what we do, we compute the maximum weight matching. So let me first tell you morally what we do, and then I'll add some tweak. So morally what we do, we compute the maximum weight matching of the graph that as we see it right now for everything that arrived so far. And if the partner of VT is available, we match it. Okay. The only tweak that we do is, remember I told you that in the analysis we have to compute the exact probability with which a vertex is available. And for this reason, we want to ensure that every time we do the matching, in every phase, we have a perfect matching. And for this reason, if we are in an odd iteration, we remove a random vertex that arrived before. So we make sure that we have an even number of vertices and we do perfect matching. And if the partner is available, we match it. That's the whole algorithm. And this algorithm gives us 5 over 12. Let me actually skip the analysis because I want to spend just a few minutes showing you that it's tight. Right, so yeah, I'm going to skip the analysis. We're doing some, calculating some expressions, doing some upper bounds, optimization, and we get this 5 over 12. So now let me spend the last few minutes showing you that we cannot do better than 5 over 12. So here is the instance that we are going to use. We are going to use a complete graph, a clique. We are going to associate with every vertex a unique natural number. So every vertex V has associated with it some natural number lambda V. And we are going to set the edge weight of the edge between vertices V and U to be n to the 3 times lambda U plus lambda V. And shortly you'll see why we choose this large number, okay? In order to show that in our cardinal setting we cannot do better than 5 over 12, we are going to use a reduction to an ordinal setting. So what's the cardinal setting? The cardinal setting is our setting where the vertices are valued. I told you we're going to associate a value with every vertex. The algorithm observes the values upon arrival. And the goal is to maximize the expected value of the matching. This is our setting, and we want to show that we cannot do better than 5 over 12. We are going to show that if we can do 5 over 12 in this cardinal setting, we can also do 5 over 12 in this ordinal setting. In this ordinal setting, the vertices are just ranked. They're not valued. They are ranked from top, from highest, second highest, etc. The algorithm, upon arrival, observes only relative ranks. We don't have values. And the goal is to maximize the probability of matching the top 2 vertices. Okay? This is more in line with the original secretary setting where we want to maximize the probability of getting the maximal value. Okay? And this reduction goes through a hybrid setting. We found it easier to do the reduction in 2 phases. The first phase is a reduction from cardinal setting to this new hybrid setting. In this hybrid setting, the vertices are valued and the algorithm observes the values, just like in the cardinal setting, but the objective is to maximize the probability of matching the top two vertices like in the ordinal setting. Okay, so first of all, we do the reduction from the cardinal setting to the hybrid setting, and here we use the choice of the weights. In other words, the only thing that matters is the top two vertices because of the way we chose the weight. And then we do a reduction from the hybrid setting to the ordinal setting using the infinite version of Ramsey's theory, showing that what matters for the algorithm is just the ranks and the algorithm doesn't use the values. And then all we need to do is to show that in this ordinal setting, we cannot hope to match the top two vertices with probability higher than 5/12. Good, so one more slide and I'm done. How do we do this? So first of all, we show that the optimal algorithm for the ordinal setting is fully characterized by a vector C in 0, 1, n. So essentially n rational numbers between 0 and real numbers between 0 and 1. And the semantics is CT is the probability that we match the top two vertices so far at time t, if possible. What do I mean by possible? It means that the top two vertices so far are available and that the last arriving vertex is one of them. So my algorithm is very simple. I have C1 to Cn, and if it's possible to match the top two vertices